Hi, this is Chris from California Cycle Works. We're going to do another video about our test benches. This time, you're actually going to just sit at my desk with me. So we're getting caught up on testing all of the TPSs that we previously tested with our old test bench. It wasn't all fancy. It didn't have a readout, and its stepper motor wasn't as good. This particular bench is about 3 times more accurate than the last one, and it gives us visual feedback of the parts. And so we're actually going through the parts that the old bench couldn't figure out were good or bad, and then now we are getting definitive results. So we take our part, plug it in, set it in place, and we go. And if the part's good, it says it's good, the graph is green, and it starts printing out the report right away. The PF3C is a nonlinear TPS, so it has a pretty steep initial slope. That way you get great resolution between small throttle openings until about 30 degrees, and then it tapers off and is real gradual to wide open throttle, which kind of makes sense. Like, if you're here, you're going fast anyway, so just pin it. And then numbers and stats, I'll have a write-up somewhere. We'll talk more about that and I'll describe things, but basically it does 119 data points that are 3/4 of a degree apart. So total rotation is 89.3 degrees from 0.122 to 5 volts. And then we do a little bit of analysis of the rise and how steep that is. And then I take standard deviation of the numbers I gathered. We detected the knee occurring. We said that 30.8. Blah, blah, blah. Anyway, it's got a great standard deviation in the first part. And it says it's outstanding on the second part. So we put him down and we make sure his TPS goes on him. And this is a wiring harness I made using the same connectors as the bike, and I got rid of the rubber gasket and I broke out the catch so it's easy to just slip on and off. Let's zoom in on the screen. That's the menu. I can pick which TPS we're testing. How many times it tries to retest if the initial one's bad. Right now I've got it set to 0. These parts are all kind of assumed to be bad to start with. We can change how quickly it goes through. And I've got like other secret settings, big deal. But you can see here on the joystick value, every time I play with it, that number changes. And that just basically tells us the same, that's the analog to digital converter value on the resistors here. And then ADC here is for the actual TPS. So through here, you can see the green gear, and I can turn it by hand. And then over here, you can see the ADC value climbing. It's a 10-bit digital converter, so basically 1024 is the max possible value. So I held the gear all the way open and it's 1023. We start letting go and it springs back and you can see it going down, but you can't really tell what it's doing. Like, you can't really tell if it's going to be linear or not just based on looking at the numbers, which is why we run the stepper motor. And then now watch, we'll get you in closer here so you can watch the stepper run. You can see the gears in here for the stepper motor. This is the stepper motor itself. I printed this on our 3D printer, and the green gear I printed on our previous one that didn't really work. Okay, so we'll run the test. Oh, and this one fails, of course. And it tried a couple times, that didn't work. So it didn't like that very much. Let's see if it'll print it. Sometimes when the response is bad, it doesn't like to print. Oh, it's doing it great. Yeah, and this part actually would normally be considered good by everyone else. If they check it here, it's like 0. If they check it up here, it's like 5 volts. They check it once or twice near the, what I call the knee, and it's good and it's good. That's the industry standard, a 4-point test. And as this shows, there are a couple more points on the TPS than just 4. Now this one only tried to get through 70 degrees, and that's because when my software detects big spikes up here, it'll end the test prematurely. So it already knew something was wrong. And then let's see, big giant spikes here, minus 100 and plus 100. The minus 121 exceeds the limits of minus 2, so it says it's bad. Standard deviation is 45, and under 6 is passable. Most of them are actually around 3 or 4. So yeah, it knows this is kind of screwed up. You also notice on our test bench, bad parts do not automatically print. So when it runs through the test and nothing happens, the operator is kind of signaled, hey, something went wrong, retest. So let's see if this test goes through the full sweep. There we go. And that's a proper full speed test. It started printing, so we know the part's good. And I actually retested the part that was good just now. And that's the stepper motor itself, this black bodied square. And then the round aluminum parts and the green part are from the last version of the test bench, and the bearings. And then through the process of getting the 3D printer working, I decided to build the rest of the test bench around it. Also designed these docks using the 3D printer and the CAD software, so they just cradle the part perfectly. Before, where these bolt holes are, we had a toggle clamp, and you had to manually clamp each one because I'm not going to carve all this out of aluminum. The modules are removable. There's a screw. It just slides right off. And these are a lot lighter than plates of aluminum were previously. This is the module for the IPF2CB. The IPF2CB is a pretty interesting character. They also have a spiked collar. So the way these are designed is that when you put them down into where the TPS shaft goes, they can't be removed. Kind of an ugly trick. So I created this sliding part here to allow us to pull the parts in and out with their spiky collar. So let's change our menu to the IPF2CB, and we'll test this guy. And of course he's good. He's one of my reference parts that I don't sell. And you saw it was a good part, printed out right away. This is a linear TPS, so you want this to be an ideally straight line. We've seen some fantastically not straight lines on parts that otherwise would be said they're good. So this dock actually was the last one I built. It's kind of the toughest. The other aspect of it is that there's no return spring inside this TPS. And so I had a problem with it. The way the stepper motor works is it turns at 3/4 of a degree, stops, checks the voltage on the digital converter, the analog to digital converter, or ADC, gets the measurement, and then it moves it and repeats. And so it does it so fast that I think there was, it needed damping because it would move and probably rattle. And so I discovered this ingenious concept of rubber bands. So I shoved the rubber band in there, and then that made its output clean up so well, and it kind of fixed that jittery problem. About the same time as also when I was working on the delay on each step to take the measurement. As for the PF09, each of the TPSs I've got marked in the dock its initial orientation. I mean, the test is kind of smart, but you know, I've got a job to do other than play around on computers, so it doesn't really figure it all the way out. So you start it off where it needs to. Oops, we're on the wrong TPS. It was that smart, at least. Let's change it to the PF09. And you can see it didn't like that one. Probably because it was laying out here, so it's a bad part. So we'll change the number of retests here back to its usual 4. So there, the operator will first find out that, hey, it's testing again. You look, see, it tries to give you a little bit of feedback, nothing like the actual test. And in this case, on the second part, the last of its many failures on this TPS was the second part detected too big of a dip. Press down to print, other key goes back. This is actually the printout that he was sitting on. And it kind of matches the bad trace, goofy, weird. It blew a few different, like 3 different ways this thing failed. And I always say this is a bad test, so in case somebody does print it out and try to sell it to you, which I hope never happens, we see it. This is the other connector type. The PF09 uses the junior timer type connector. Yeah, a little bit of work went into that, but the last thing I want is for a shop to get a part, and then if it's one of these goofy parts, it might take you hours to figure it out. So this guy's got kind of an interesting little behavior. I saw a little bit of a trend of the failures. It's like they clocked the resistance wrong inside the TPS. So this happens too late or who knows what. And then it blew a couple of the tests, so you had to manually print it. That one's pretty fantastic. Yeah, imagine this could have passed a normal OEM test. They say it's a 4-point test, so you do somewhere down here when it's closed, and you open it all the way, and you check up here. And normally, once you bury them all the way, they go to 5 volts, so that would pass. And then you check 1 or 2 spots in between. And unless it really is critiquing the voltage in here, like exactly the number, you'd never know. And I don't think you could just look at the numbers and know if you didn't have something this precise, counting each step, knowing what degree you're at. And so this one blew 4 of the different tests. Let's see what other excitement we've got. That one just ended a little early. Yeah, this one ended a lot early. That would suck to have. But then again, it's just telling the bike you're pinned all the time. I've heard a few chips for 916s were just all ones anyway on the gas. You're seeing the trend. Oh, here's an exciting one. Who knows what that would do? And the first question, you know, when I critique people when they make parts, is they say, well, did you try it and how did it run? And I'm like, well, I'm not gonna subject somebody to this crap. It's a lot of work to change a TPS. There's a cool one. So those are examples of what we catch doing this testing of parts that otherwise would have been called good using normal practice. And this normal practice, the 4 points, you know, open, or was it like no throttle, full throttle, 1 or 2 in the middle, that's the same for parts that come from any continent. Our test is so strict that OEM parts sometimes don't pass. We have the PF1C that came out of my bike from Magneti Marelli. Actually, it had a dip in it that failed it. I didn't really notice. I'm not going to take apart my gizmo, but I'll tell you what's in it. It's using an Arduino type of platform, but it's not an Arduino powering it or being its brains. The display is part of a card that has the joystick and a reset button. This is from Adafruit. It's their 1.8 inch TFT with joystick, and it's got an SD card, but I don't need that. The bottom board, this red board, is a ChipKit UC32. So it's got about 10 times the horsepower and storage as a normal Arduino, which I found out I needed to dynamically print out the graphs. Storing this in memory is 19K, because it's 384 by 384, and it's all ones or zeros. And then each time it takes the data points, it goes through and plots a line between the points in memory. And then when it's done printing, it goes back and empties that memory back out, so it's blank. And then it draws a frame. I think that's a 2 or 3 pixel frame. It draws 3 lines actually. It does the first line, you can't see it, and then it adds 2 more lines underneath it, and then that's thick enough to where enough heat comes out of the head of the printer that it'll burn in and make a mark. The middle board here where you see this is the 5-volt connector feeding the chip kit. This middle board is a prototype shield. Those are designed so that they have the pins to connect between the chip kit itself and the different shields. And then this makes it to where you can wire up weird things like my 2 connectors for the TPSs. I've got power feeding the chip kit. I've got, that you can't see, there's a connector with 4 pins driving the stepper motor. There are 2 more connectors on here that go down and run the printer. And then it's yet another connector runs the real-time clock, so I've got the time of the test that prints. And then I've got inside here a power supply that feeds 5 and 12 volts. And then another converter takes the 12 and makes 9 volts for the printer. So that was a little bit of a fun deal to make. The USB cable is an option. I'm about done with the umbilical because I'm about done testing. This I'm using to program the chip kit, but also to get feedback. This is the debug code the chip kit sends back to the computer while the test is running. And so it's a little bit of debugging stuff to let me know what it's thinking in case I need to come back and figure out what's going wrong. And so it discovers what it calls the start. That's once the voltage starts changing. So when the throttle position sensor is all the way relaxed, it stays, it doesn't start right away, and then when it's installed on your bike, the throttle position sensor is held open a little bit, so to make sure you get into the curve, as it were. So it finds the start, so it re-indexes the test data, and then every 3/4 of a degree it runs another point. So it's like 124 data points. That's when it detects the knee. In this case, it found a spike at the 49th data point where the rise from one point to the next was actually -4. And then some statistics on the numbers. I use this when I'm going back and retesting ones that fail just to see what's going on. So good parts in here will, like when you have a good TPS you test, there's not very much. You'll just get the running analysis stats. It'll tell you a start, and then there won't be any spikes found. Or if there's other issues, it'll scream about those as well. And there's the screen for that exact test. And so testing, the skip detector went, that's interesting. And then it retested, and then it said whatever the last error of all of them was, the standard deviation was too high. And so press down to print or doing anything else doesn't, well, we've already printed him a few times. And the test bench is set up to when you disconnect it, it's the same as hitting any key. That way you're ready for the next part. So that's the new TPS test bench, the visual or version 2 test bench. Pretty hardcore, committed to quality, and I think we're the first person on the planet to give a printout with every TPS we sell. And so they're definitely worth your time and peace of mind. I'm Chris Kelly. Thanks for watching.